Made it on time this time.
You're pretty early.
Sir.
No,
Hey, how's it going?
I wanted to ask, how do we know if we have an advising, like, if we have to do advising?
So if your campus-wide ID is even, then you probably have an advising appointment, unless you met with advising last semester. So advising is once per year, but you can go to your student account and see if you have a hold. So if you have an advising hold in your account, then you need to do advising.
Okay.
Yeah.
And then I've heard you teach 410.
Mhm.
How is that?
You mean, how is the class
Yeah,
itself?
how's the class?
Yeah, it's so in that class, it's about finite element analysis.
Uh-huh.
So in that class, we learn a software called ANSYS. So usually what I tell people is that after you design a part in SolidWorks, the next thing you want to do is you want to find out if the part's going to, how it's going to work in practice. And so you can run a simulation, you can put forces on it, constraints, you can get things like, how much is the part going to deform, what's the stress distribution going to be like, what's the factor of safety. I mean, you can do all those things in finite elements without having to actually like build a part. So it's very complementary to like SolidWorks. And so if you really enjoy SolidWorks, you enjoy kind of designing things in the computer, I say finite elements is kind of a good follow-up class for that.
And there is another one. Just because I'm doing my classes,
Okay. Mhm.
and some of the classes I've never heard of.
Mhm.
So I'm like, let me ask you.
Yeah.
I have no
Now, I will say, so
idea.
the electives that are on there right now, it's a preliminary list right now.
Uh-huh.
I think some things will probably change when we get closer to registration. Because a lot of those electives are exactly what we offered last year. And usually we change it up every year. So some may be there, some may not. Finite elements probably has a good chance of being there just because it's popular class, but.
Well, there's, yeah, so finite element is already on there,
Mhm.
and then it was 454 optimization.
Oh, okay. Yeah. So that's the other elective I teach in the fall. So optimization is more about, it's a computer programming class. And so if you're really comfortable with MATLAB, I think you'll really like that class. So that class is all about, how do you take a design? Because a design is usually comprised of quite a few parameters. So like, the lengths of certain things, like the amount of power you can put. And optimization, how do you choose those parameters to really kind of, get the most performance out of your design as much as possible? So it's kind of a combination of like, there's basically some mathematical algorithms that you can utilize to optimize designs.
Mhm.
So it's like a combination of like applied math, programming, and engineering. But it is very program heavy. So I do warn students about that.
And then, well, because that's a 4 o'clock class, and the
Yeah.
other 4 o'clock. Oh, no, that's 454. Never mind. Oh, wait, no, 452.
452, that one is, tell me the name of that course again.
Fluid
Machinery.
machinery.
Okay. That one I don't know too much about. Just because usually those are taught by kind of part-time faculty and our schedules don't really line up.
Okay.
But what I understand from that course is that if you like fluid mechanics, then that course is kind of good to that. And that course is focuses a lot on kind of a lot of big machinery that utilize fluids like turbines, wind tunnels, valves, things like that. So it's like fluids, but more applied. That usually what I tell people.
Okay. Thank you about that coding one, because I don't like that. I don't.
Yeah. I warned, because some people come in the fall and they're like, oh, this is coding. I don't know if I like this. So yeah, I try to be upfront with people about that. So.
Thank you.
So for that class, the coding class,
Mhm.
you build off assuming that the students already know basic coding, or
I review a little bit,
But a little bit, right?
but having a strong background definitely helps, just because there's a lot
yeah.
we have to cover.
So what would you recommend to get like a stronger background? Because Like the only MATLAB class I've had is that one.
It's a 205.
And
Yeah,
that's it.
yeah, yeah.
Everything else has just been practice and then hopefully it works.
Yeah, so that's with MATLAB, you kind of just have to kind of just do a lot of practice yourself. So, you know, there's a lot of, I would say kind of online tools, even if it's not explicitly MATLAB. I tell people programming is pretty universal in terms of what language that you use, because all of the logic, all kind of the ways of thinking is the same. So I think there's a lot more resources nowadays on Python. And so if you look up kind of Python workshops and if you learn kind of some basic Python, get used to doing that, because the loops are the same, the variables are the same. If statements are the same in every language. And so if you get used to that, then all that really translates to MATLAB.
Okay.
Yeah.
Was there a class that was very difficult for you?
When I was in school,
Yeah.
I actually really struggled with the design course actually. So we had a senior design course. I was a very good textbook student. But when it comes to like thinking outside the box, I think I really kind of struggled with that a lot.
I didn't.
Yeah, I did not. Yeah. Our senior design project was to kind of build this little robot. Yeah, ours did not work.
That's when
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. It's the last class before spring break. How's everyone doing? Good. Glad you guys are here. I'm contractually obligated to be here, but of course, you know, the fact that you guys are here is means a lot. So thank you guys for coming. Okay, so today we are going to continue our lecture on free convection. So last time we introduced this idea of, you know, having it's actually possible to get convection heat transfer even when your fluid is still, even your fluid is stagnant. And that's purely due to buoyancy forces. So we'll continue that discussion today. You know, we'll do a couple of examples so you can see how this works. And then I will see you guys off to spring break. All right, so only announcement I have is that homework 5 is out there right now. So make sure you guys are looking at that. You guys should have everything you need to do homework 5. Homework 5 is just based purely on internal convection. So basically what we finished covering on Tuesday. And so definitely take a look at that. You do have some time after the spring break to get it done. But you know, it is, you know, just a regular homework assignment like everything else. So, you know, leaving until that last couple of days may not be, you know, may not be wise, at least for today, at least for tomorrow, while we're still kind of in session. I would definitely take a look at it and then, you know, ask any questions that you have, right? So over spring break, you know, I'm not planning on having office hours over spring break. But I will be available. And so if you do have questions, if you're looking at homework 5 over spring break, or if you have questions on the upcoming midterm or advising or anything like that, you know, I will be at my email. So you can just send me an email over spring break and, you know, and we can chat. Okay. Yeah.
Sorry, quick question. What's the midterm again?
Midterm will be, that's a great question. It's not the week we come back. I think it's the week after the week we come back.
So 2 weeks after spring.
Exactly. Yeah. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. We'll pick up where we left off on Tuesday. Okay, so let's talk about free convection. So free convection, this is what's better known as what I call buoyancy-driven convection. And so free convection is based kind of solely around the idea that, as you heat up a fluid or as you cool down a fluid, the density of the fluid is going to change, right? And so if you have, say a situation like this where you have a vertical plate, right? We'll assume just for now that the plate is heated. So we'll say that the plate is hot. Okay. We'll talk about a situation later today when the plate is cold. Okay. And so what that's going to do is that's going to heat up the fluid in the immediate vicinity of the plate. Okay. Right. And one thing we know is that as the fluid heats up, its density is going to go down. And so as the density of the fluid goes down, what it will do, just like you see in a hot air balloon, right? We know that hot air rises. That's not exactly correct. Hot air just gets less dense. But the net effect of that is that you're going to have an upward velocity. Okay. And that upward velocity is driven just purely by buoyancy effects. Okay. And all of a sudden, even though we started with a fluid that was completely stagnant, that was completely still, we actually do have some fluid flow. So we have some motion of fluid that's going up. And whenever you have heat transfer to a fluid and the fluid is moving, then we have convection heat transfer. And so this whole chapter, this whole week is kind of dedicated to kind of analyzing these types of situations. How can we quantify this amount of convection? So we'll be computing convection coefficients, okay? And then using those convection coefficients in our heat transfer problems, okay? And so just like we've always been doing for the last 3 weeks, right? The way that we obtained convection coefficients is by computing its Nusselt number. So it's the same kind of thing that we've been kind of talking about this whole time, right? Because we know that the Nusselt number is equal to convection coefficient multiplied by some characteristic length divided by the thermal conductivity of the fluid, okay? And so if we can compute this Nusselt number, then we'll be able to compute the convection coefficient, okay? Now, our process of computing the Nusselt number in this case is going to change slightly, right? So usually when we compute the Nusselt number, right, we compute the Reynolds number first because there's usually some kind of correlation that relates the Nusselt number to the Reynolds number as well as the Prandtl number, right? So this is what we usually do. So we say Nusselt number is some function of the Reynolds number and the Prandtl number, okay? So those are all of the, I would say at this point, maybe, 6 or 7 different correlations that we have for the Nusselt number under different scenarios, right? Okay. But with free convection, if you remember from end of class on Tuesday, we can't compute the Reynolds number because our fluid is technically stagnant, right? And so instead of the Reynolds number, we're going to compute the Grashof number, which is given by GR, okay? So for free convection problems, the Grashof number is basically going to play the same role as the Reynolds number. Okay. Okay, and so in fact, you know, I did kind of flash the correlations at the end of class last time. So I'm just going to scroll up just so they can see it. You know, but you don't have to write it down again, just because it's just the same as what we had last week. So if I go back to the end of the notes last week, you know, we had these two correlations for the Nusselt number as a function of the Grashof number, right? And so if we have laminar flow, our Nusselt number is equal to 0.59 times the Grashof number times the Prandtl number raised to the 1/4 power. Okay. And then for turbulent flow, we have that the Nusselt number is equal to 0.1 multiplied by the product of the Grashof number and the Prandtl number raised to the 1/3 power. Okay. And for free convection, the way that we determine whether our flow is turbulent or not is if we take the product of the Grashof number and the Prandtl number, and if that is greater than 10 to the 9th power, then we have turbulent flow. Okay. Okay, so these two correlations here, these are going to form kind of the basis, at least for the first example that we're going to do today. Okay, but that was just kind of a review of kind of what we went over last time. Any questions on this so far? Okay, good. All right, so before we do an example, I do want to kind of mention one thing. And so I may have mentioned it last time, but you know, the thing about free convection is that a lot of times, you know, we can neglect it. Right. In fact, you know, up until this point, so we're in week 10 of this semester, so we've gone 9 whole weeks of this semester, and you know, this is the first time we've even mentioned free convection. So you know, that probably gives you an idea of how important this is on a practical basis. Okay, especially when you have some kind of forced convection, and then in those cases, you know, you're probably going to neglect the free convection. And so if you have some kind of fluid velocity, either external flow, internal flow, that's probably going to dominate the convection heat transfer, and free convection can be more or less neglected. Okay. But there's actually a way that you can determine or to kind of, you know, actually quantify, you know, how strong each factor is. Okay, so if we want to quantify kind of the relative strength of each of these convections, we can compare both of their non-dimensional numbers. Okay. So the main non-dimensional number for free convection is the Grashof number, and the main non-dimensional number for the forced convection is the Reynolds number. Okay. So we have free convection and forced. So free convection, we have the Grashof number, and for forced convection, we have the Reynolds number. Okay. And so one way that you can compute them is you can just simply take the ratio, right? So if you take the ratio of the Grashof number divided by the Reynolds number, okay? And then depending on the value of this ratio, you know, you can tell, you know, which one's going to be greater or not, okay? Although we have to modify this ratio a little bit. And it kind of seems like we're kind of cheating in terms of, you know, making things better for forced convection, but this is based purely just on how the non-dimensional numbers are defined. And so the ratio that you actually want to take is you're going to take the ratio of the Grashof number over the Reynolds number squared, okay? Okay, and we basically have kind of three situations that can arise from this, from the value of this ratio here, okay? Okay, so let's look at a situation when this number is much, much less than 1. Okay, so we have basically a denominator here that's going to dominate. Okay, so this is what's going to happen in most cases. And so when this ratio of the Grashof numbers and the Reynolds number is much smaller than 1, then what we can say is that forced convection is going to dominate. And so forced convection, question, yes.
So this is to determine whether your flow your flow is free convection or forced.
Exactly, yeah. Yeah, so in the case when this ratio is much, much less than 1, we just ignore free convection. And you basically just use the exact same kind of methods that we went through kind of the last couple weeks. So you compute Reynolds number, Nusselt number, convection coefficients, same as before. Okay. The opposite situation is that if this ratio is much greater than 1, right? These do happen, and so this does happen, and we'll talk about certain situations where this can happen. But in this situation, we have free convection that dominates. Okay. And so in those situations, you would ignore the forced convection. Okay. And so in these situations, you would use kind of the techniques that we're going to go over today, in the couple of examples that I have planned. Okay. But you can also have a situation where this ratio is approximately equal to 1, right? So it's, maybe 1, maybe 5, maybe 0.7, 0.3, kind of somewhere in that ballpark. Okay. And so in these situations, neither of them dominates, and both are going to contribute to the convection heat transfer. And so in these situations, when both are kind of equally important, you kind of just say, well, this is complicated, and we have to do this with a simulation probably. So these situations are pretty complicated. And I don't know if there are any kind of good hand calculation or analytical methods that exist for computing situations which are, both have free convection and forced convection. Those situations, you probably need to run some kind of simulation to determine what's the best. Yeah.
Are we running any simulation in this class?
No, we're not. So this class is mostly just on the theory. Yeah.
Can we bug you now to try it?
I mean, yeah, you could. I mean, of course you can. But even I don't have that much experience with this stuff. But I will try to figure it out with you, and see how far we can get. Okay, so of course, that last situation, we're not, we're obviously not equipped to do that in this class. And so we're either going to be most time we're going to be in the regime where forced convection dominates. Sometimes we'll be in the situation where free convection dominates. So you just have to kind of determine which one, is going to be the case. All right, any questions on this? Yeah.
Under what scenario would free convection be dominant?
Yeah, that's a great question. So free convection, if you look at kind of the structure of the Grashof numbers, let me write down the formula for that again. So Grashof number is gravity times the thermal expansion coefficient times the difference in temperature. So that's Ts minus T infinity times some length cubed time divided by the viscosity squared. Okay. So free convection is going to dominate when this Grashof is of some really high value. Okay. Now the most obvious case where free convection dominates is that if there's just no forced convection at all, and so if the fluid is just naturally stagnant, there's no velocity, then in those situations free convection is going to dominate, just because the other team just doesn't show up, and so you automatically win. But in a situation where there is some forced convection, it is still possible for free convection to dominate, right? And the main most common cases where that happens is when this quantity here is extremely high. Okay, so that quantity there is the difference in temperature between the surface and the fluid. Okay. And so if you have situations where you have really extreme differences in temperatures, you have an extremely hot solid and a very cool fluid, those are situations where you're more than likely to see free convection play a much bigger role. Okay? But if the temperature differences between your solid and your fluid are somewhat modest, then probably forced convection is going to be kind of more important in those cases. Yeah. Mm-hmm. Actually, the example we're going to do today is like that exact. Yeah, question.
Is that why some crazy stuff can happen when you throw like what if you throw in volcanoes and they like
Oh yeah,
bounce around and explode?
Yeah,
Something
yeah.
really cold, or
It's-
is it a certain metal or
It's part of it. I mean, when you have really extreme temperature differences, just a lot of really crazy things happens. You have just a really rapid phase change. That's probably the most extreme thing that
trying to think
happens.
how like buoyancy would affect through something really
Yeah.
hot and
Yeah, it's part of it, but probably only a small part of throwing something in a volcano. So there's probably a lot of other stuff going on at that point. Yeah. Mhm. All right. Any other questions before we jump into an example? Okay. All right. Oh, actually, one thing before we jump into an example, just to make our lives a bit easier, let's introduce another non-dimensional number called the Rayleigh number. Oops, I'm starting using red.
It's the same repeat as a nozzle flow.
I'm not sure actually. It might be. But this one's more about I'd have to look that up and see. I'm trying to think of, because I know that really, but then I'm trying to see if this is the same one that attributed to this number. But yeah, I have to look it up. But honestly, the Rayleigh probably shouldn't get credit for this because it's kind of a really simple thing. So if you look at our Nusselt correlations, let me kind of go back up here so you can see, right? So these are the two Nusselt correlations that we're going to be working with, right? If you look and see how these Nusselt correlations are kind of designed, or how they've come to be, Grashof number and the Prandtl number kind of always appear together. And they always have the exact same exponent as well. And so that's why, we have this. And so what Rayleigh said is that, all right, since these guys are always together, let's just combine them into one. And then let me put my name on it and become famous for it. So that's what Rayleigh said. So the Rayleigh number, we call it RA, is simply just equal to the product of the Grashof number and the Prandtl number. That's it. So it makes your Nusselt correlations a little bit more nicer. And so actually, most of the time you'll see the Nusselt number correlations. And so, for instance, you'll have 0.10 times the Rayleigh number with respect to length to the 1/3 power. Okay. So it makes it really clean. But it's not really contributing all that much, because taking two numbers and multiplying them and then putting your name on it, is not that significant, I would say. Okay. All right. So with that out of the way, but I did want to mention that just because most time you'll see the Nusselt correlations with respect to the Rayleigh. Okay, so let's do an example. Okay, so with this example, let's say that we're looking at a fire protection glass. Okay. So oftentimes, when you have, either in labs or, certain test equipment where, you're going to be producing very hot temperatures on the inside, you have to have fire resistant glass to protect the people on the outside, right? So let me just model it as kind of a vertical plate. Okay. So that's our fire protection glass. And then let's say on the left-hand side of this, we're going to have some explosion or some fire. Okay. Okay. So of course, that's going to heat up the glass, right? And so let's say that this heats up the glass to an extent where the surface temperature at this glass is 232 degrees Celsius. Okay. So extremely hot to touch, and that's going to cause, air to kind of go upwards. Okay. And let's say that on the other side, right, on the right side of this glass, that's kind of where humans are designed to be. We'll say on this side, we have ambient air with a temperature of 23 degrees Celsius. Okay. Okay. Let me give you some dimensions here. So let's say that the height of this glass here, we'll call it L, is 0.71 meters. Okay. And let's say that the width of the glass, so basically the depth of the glass going into the page, is 1.02 meters. Okay. Okay, so if we assume that the ambient air inside the room is relatively stagnant, okay, so that's a term you'll see a lot in these problems. So usually when you see either stagnant flow or stagnant air, stagnant water, that basically means that you can assume that forced convection is not present. So in the case of kind of stagnant flow, the only way that you can get convection heat transfer is through free convection. Right? And so if we assume that the air in the room is stagnant, let's compute the amount of convection heat transfer from the glass to the room. Okay? So in other words, we're going to be computing Q. Okay? And it's going to be Q convection. Okay. All right, so that's the situation for this problem. So the way we're going to solve it is, in order to compute Q convection, we have one formula that we've used, probably a couple dozen times already in this class, Newton's law of cooling, right? So we know convection heat transfer is going to be H convection coefficient times the surface area times the difference in temperature between the surface and the fluid, okay? HA times TS minus T infinity. We have everything in this equation. We know the two temperatures, we know the surface area of the glass because we know its dimensions and we assume it's rectangular. Of course, the only thing that's missing here is the convection coefficient. And so what we're going to do is we're going to apply our convection problem solving recipe to solve for H and then use that to solve for this Q here. Okay. All right, any questions on the setup for the problem? Okay, all right, so let's go ahead and set about to solve for H. Okay, so we have a 5-step process for this. Right, so first step in our convection problem solving methodology is to identify the geometry and the type of flow that we have. Right, we have, quite a few Nusselt number correlations to choose from at this point. I think we have maybe 6 or 7 at this point. And so choosing the right geometry and choosing the right nature of the flow is going to be important for making sure that we choose the right correlation. Right? And so in this case, we have free convection. So we already know based on the problem that forced convection is not going to be present. And so we have free convection on a vertical plate. Okay, good. All right, step two. So step two is we're going to, we need to get the properties of the fluid at the film temperature. Properties. Okay. Okay, so we're not given a film temperature in this problem, so we need to compute it, right? So film temperature, TF. That's going to be the temperature that we evaluate the properties at. And so we're simply just going to take the average of our surface temperature and the fluid temperature. So this is TS plus T infinity divided by 2. Okay. So we know the surface temperature is 232 degrees C. Our air temperature here is 23 degrees C. So we add them up, we divide by 2, we get 127.5 degrees Celsius. Okay. And so now we know the fluid. So in this case, our fluid here is air. And so we're going to look up the properties of air. At 127.5 degrees C. Okay. Okay, so let's go ahead and look those up, but I already looked those up for you because I already did this example. So the thermal conductivity of the fluid is 33.8 times 10 to the minus 3 watts per meter Kelvin. We have the value of alpha, which is the thermal expansion or thermal diffusivity. That's 38.3 times 10 to the minus 6 meters square per second. I don't know if we're going to use that one, but I did compute it here because I think we already have the Prandtl number anyway. Okay. All right, we have the kinematic viscosity, nu, that's 26.4 times 10 to the minus 6 meters square per second. We have the Prandtl number of air at this temperature is 0.69. Okay. Okay, so all of those properties you would look up in the table. Okay, question, yes.
What is the units for alpha? Is that the same units for kinematic viscosity?
It is, yes. So this alpha here is actually used to compute the Prandtl number. So I think that may have been why I did that, because Prandtl number is nothing more than just nu divided by alpha. But typically these data tables will give you Prandtl number directly, so you don't need to do that. So I think maybe for this problem I just listed both because they were in the table. So, but if you're given Prandtl number, you don't need alpha.
Is it like who will ever have to find alpha?
Probably not in this class because for most well-known fluids like water and air, then the Prandtl number is pretty well documented. So you would just be given Prandtl. Yeah. Okay. There is one more property that we need at this point, and it's not in the data tables. Okay. And so if you look at our formula for the Grashof number, there is this kind of mysterious parameter beta. So beta is something that we need to compute the Grashof number. And beta was the coefficient of thermal expansion. Okay. Basically, it's a measure, or it's a coefficient that tells you how quickly this fluid will expand as it's heated up. Okay. It's a measure of how quickly the density changes. So this coefficient is not directly measured. It's not directly tabulated, so you can't look up in a table. So we're gonna have to approximate this. But luckily, the way that we approximate this beta is we just take 1 divided by the film temperature. But you have to be careful here because this film temperature that we plug in has to be in kelvins. Okay. You want to be careful about using this this formula here. So when you do 1 over the film temperature, make sure to convert the film temperature to Kelvin, and then you can kind of plug that in. Okay. So up until this point in the class, you know, I've kind of said it doesn't really matter if you use degrees Celsius or Kelvin. From here on out, you know, we are going to see situations where it is going to matter. So this is kind of the first case here where it matters that you use Kelvin. And then later on in the very last part of the class, when we do radiation, it's going to matter there as well. Okay, so just make sure of doing that before you compute beta. Okay. And so if we do that for this case, so to get Kelvin, we just take our temperature in degrees Celsius and add 273. And so our film temperature in this case is 400.5 Kelvin. Okay, so that means our beta value here is going to be 0.0025. And the units are just 1 over Kelvin. Okay. Any questions on the air properties here? Okay, good. All right, so now that we have all the properties that we need, let's move on to step 3 of our methodology. So this is where we compute our Reynolds number. Okay. But since we have free convection, we're not computing the Reynolds number, right? Reynolds number is not relevant here. And so instead, we're going to compute the Rayleigh number. All right, so the Rayleigh number is equal to Grashof number multiplied by Prandtl number. Okay, so let's plug in for the Grashof number. So we have G times beta times the difference in temperature, Ts minus T infinity, multiplied by L cubed, divided by the kinematic viscosity squared. And we're going to multiply this entire thing by the Prandtl number. Okay, so we have everything here. So, you know, gravity here is just, you know, we're in SI units. So gravity is going to be 9.8 meters per second squared. Beta, we just computed up here. Temperature difference, we have that already. The length and the viscosity. And so we plug everything in. We get 1.813 times 10 to the 9th. Now we have to determine, now that we have our Rayleigh number here, we have to determine whether our flow is laminar or turbulent. Okay. And so our criteria for laminar or turbulent in free convection is we have to check if it's greater than 10 to the 9th. Okay. And so since this number is greater than 10 to the 9th, it is kind of just slightly bigger than 10 to the 9th, then we have turbulent flow. Okay. All right, any questions on this part here? Okay. All right, so now that we have our Rayleigh number, let's go ahead and compute our Nusselt number. So we know we have free convection. We know we have turbulent flow. So this is just, you know, plugging in the formula that we have, right? So for turbulent free convection, our Nusselt number is equal to 0.10 times the Rayleigh number to the 1/3 power. Okay. So this is simply just kind of plug and chug here. And so once we kind of plug in this number here, So 1.8 times 10 to the ninth is ginormous, but when we take only we raise it only to the 1/3 power, it reduces this quite significantly. And so our neutral number in this case is 121.94. Okay. All right, and now that we have our neutral number, we can then use it to compute our convection coefficient. Okay. And so we take advantage of the fact that the neutral number is equal to H times the length divided by the thermal conductivity of the fluid. Okay. And so we solve this equation for H, we get neutral number, just like we've done, quite a few times already. Neutral number times the thermal conductivity of the fluid divided by the length. Okay. All right, and so in this problem, we had a very extreme temperature difference. So we had a piece of glass that's over twice the boiling temperature compared to kind of normal air. So it's very extreme. But like I said, free convection oftentimes does not produce that high of a magnitude of convection, and you're going to see that here. So because the convection coefficient that we get with this extreme temperature difference of over 200 degrees C is only 5.8. We have 5.8 watts per meter square. Okay. Now that we have our H, it's kind of a long journey to get here. Let's kind of scroll back up to the problem, right? So the reason we were solving for H was that we needed it to compute the convection heat transfer. Okay. Okay. So now that we have H here, we can finally compute Q convection is equal to H times A times Ts minus T infinity. Okay. We have H, we know the surface area here. This is simply just equal to the length times the width. Okay. Temperature difference we know as well. And so the heat transfer here due to convection is 877.88 watts. Which is not that much, right? And so free convection, it is relevant here. So you do get some you do get some heat transfer due to convection, but it's not too much. Okay. All right. Any questions on this problem here? Yeah.
Were you assuming a unit width of 1?
No. So it was about 1, but there was the width given in the problem. It was 1.02. Yeah. Mm-hmm. It was practically 1.02. All right, any other questions on this problem here? Okay, so one important thing to keep in mind is that this is purely just the heat transfer that's due to convection. Now, if you have such an extreme temperature difference between a solid and a fluid, remember there's going to be heat transfer due to conduction as well, right? So the fluid is a medium just like anything else, and so there's going to be some additional conduction heat transfer, and probably in this case that's probably going to be more significant. But just if you're looking at the heat transfer that's purely based from convection, that's what this is. That's what this is here. But just be aware that there's more at play here, and honestly, probably with such a high temperature, you probably have some radiation as well. Radiation is probably going to be significant too, especially with fire, just because that's the main way that fire kind of heats things up is through radiation. Okay. Okay. Good. All right, so let's start to look at kind of some more interesting scenarios, because we've only really considered free convection when our solid is much hotter than our fluid. Right. So let's look at other free convection scenarios. All right, so let's do the obvious one first. So let's look at our vertical flat plate, but instead of having it be hotter than the fluid, let's have it be colder than the fluid instead. Okay. So in this case, our actual geometry is the same. Okay. So we have a flat plate, but instead of being hot, our plate here is going to be relatively cooler than our fluid. Okay. Okay. So of course, what that means is that the fluid next to the plate is going to cool down. Okay. And as the fluid cools, it's going to get more dense. Right, and then as the fluid gets more dense, it's going to start to fall, right? And so you're going to have a downward flow instead of an upward flow. Okay. So physically, it is going to change things. So you're going to have a downward flow. So the fluid's going to go kind of sink downwards instead of coming up, right? How does this affect our Nusselt correlations? Okay. And so you would think that, when you have kind of a change in direction here, you have fluid kind of falling down as opposed to rising up. You would think that's going to affect kind of how we do things. Well, luckily for us, it doesn't. And so this actually does not change anything, or at least in terms of our Nusselt correlations. Okay. So the same two Nusselt correlations that we went over today, so the laminar version and the turbulent version, you can use the exact same ones for the situation as well. So the direction of flow doesn't really matter, which makes sense, right? And so, when we went over external convection, internal convection, maybe just by the way I kind of drew the figures every time, it kind of seemed like the flow had to go from left to right. But if you looked at it from a different perspective, you have the flow going from right to left. And so the direction of flow doesn't really matter all too much, at least when the flow is parallel to the plate. So if you have a cold plate and a hot fluid, you can use the same correlations as we have. Right? But it is important to note that the direction of flow does change. Okay. So that's good. So, for a cold vertical plate, we don't have to kind of change anything, anything of what we do. All right. Now let's look at a different geometry. So let's look at a horizontal. All right, so actually, I think the kind of the image that I drew for you when we first introduced free convection last Tuesday. We use horizontal plates, right? Okay. Now, horizontal plates are interesting. They're interesting from the perspective that because gravity is always going vertically downwards, right? So the direction of gravity kind of naturally determines the direction of our flow, right? And so, because free convection is always driven by buoyancy, you're always going to have vertical flow to some degree. You're going to have vertically upflow or vertically downwards flow, right? Okay. So for a vertical plate, it doesn't really matter if you're going up or down because the flow is parallel to the plate at that point. Okay. But for a horizontal plate, it does matter, because you can have a situation where, let's say, our plate is hot. Okay. Right, and so if our plate is hot and it's below our fluid, right, that's going to cause the fluid to rise and thus go away from the plate. Okay. Whereas if you had a cold plate, right, a cold plate is going to make the fluid more dense. And so more dense fluid is naturally going to fall and go downwards. Okay. And so in this situation, you're going to have fluid going towards the plate. Okay. And in this situation, it actually does make a difference whether you have flow going towards or away from the plate, is because it's going to change the nature of the flow patterns, you know, within close to that plate. Okay. And so what you're going to see in a couple minutes, that, you know, we're going to have different Nusselt correlations for flow going towards a plate and flow going away from a horizontal plate. Okay. But before I show you those, let's look at a kind of a similar situation. Let's look at another horizontal plate, but let's say that we have a horizontal plate that's going to be above the fluid, so the fluid's going to be below it. Okay. So you have a horizontal plate here. Our fluid is now below it. Okay. Let me do the same thing I did there. So let's make, you know, one side of the plate cool and the other side of the plate hot. Okay. And we're going to see kind of the relative directions of the fluid in this situation. Okay, so let's do the hot side first. So for hot flow, right? Hot, you know, heat is going to make a fluid less dense, and so it's going to rise. Okay. And for all these situations, just be aware of kind of the direction of gravity. Okay. Okay, so hot fluid is going to rise upwards. Right? It's going to go in the opposite direction of gravity because it's becoming less dense. Okay. But look at the situation. So if our fluid is actually below our hot plate, then our fluid in this case is actually going towards our plate. And it's going to be opposite for the cold side. So the cold plate is going to cool down the fluid, and so it's going to become more dense. And so the fluid is going to go you know, downwards. But in this case, if the plate is above our fluid, then our fluid is going to go away from the plate. Okay. And so let me actually zoom out. You can kind of see both at the same time. Okay. So when you're dealing with the horizontal plate, you know, you have to be aware, you know, first of all, whether your plate is hot or cold relative to the fluid, and whether your plate is either above the fluid or below the fluid. Okay. Because that's going to change whether the flow is going to go towards the plate, towards the solid, or away from it. Okay, so this is definitely one kind of image here to kind of remember, because, you know, it does get confusing. Hot, cold, towards, away, above, below. So, you know, just kind of make sure it's kind of nailed in your head. Okay. Okay. And so based on that information, let's write out our Nusselt correlations. Okay. So these are Nusselt correlations for free convection on a horizontal plate. Okay. And again, they're going to depend on whether the fluid is going towards the plate or away from the plate. Okay. It doesn't necessarily have to do directly with whether the plate is hot or cold. It's the direction of the fluid going either towards it or away. Okay. Okay. So let's look at the towards first. Okay. So if we have fluid going towards our plate, then our Nusselt correlation in this case, Nusselt number with respect to L is equal to 0.52 times the Rayleigh number with respect to L raised to the 1/5 power. Okay. So luckily for for towards the plate, we just have one Nusselt correlation. Okay. And so this is valid for both laminar and turbulent. Okay. Okay. So towards the plate, pretty straightforward. Now let's look at the situation where we have flow going away from plate. Okay. So we have two correlations in this case. And so first we have Nusselt number with respect to L is equal to 0.54 times the Rayleigh number to the 1/4 power. Okay. And so this is when you have fairly laminar Rayleigh number, but it uses a different threshold here. So this is if Rayleigh number is between 10 to the 4th and 10 to the 7th. Okay. The other Nusselt correlation that we have in this case is 0.15 times Rayleigh number to the 1/3 power. Okay. And this is for more turbulent cases. So this is when Rayleigh number is between 10 to the 7th and 10 to the 11th power. Okay, so we've added 3 more Nusselt correlations to our pantheon here. So I think we're up to like 10 or something like that. Okay. Yeah, so in this unit here, it's very easy to get confused with all the Nusselt correlations. So just make sure that you know kind of which situations you need to use which Nusselt number. Okay. So one last thing before we do an example. So both the Nusselt number and the Rayleigh number here, you need some kind of length to compute those numbers. Okay. And the natural thing that you would want to do is that you would maybe want to compute the length of the horizontal plate itself, right? And so maybe you want to compute maybe this length right here. Okay. That would be kind of the natural thing to kind of plug in. But you have to be careful here because that length is actually not in the same direction as heat transfer. Because, in both cases, right, heat transfer is going vertically out of the plate. Right? So we need some kind of length scale that's in that direction. So we need a length scale that's kind of perpendicular to that plate. Okay. And so for this one, we actually use a special length scale. Okay. You only use this length for horizontal plate free convection. Okay. Well, I guess that's not true. We've seen a formula like this before in the past when we were computing things like the BO number. Okay. But the appropriate length scale to compute here is the ratio of the surface area, AS, divided by the perimeter of our plate. Okay. So just kind of be careful about that. And so, make sure you're kind of be aware of, that length scale to plug in for that. Okay, any questions on this before we do one final example for today? Okay, all right, so this will be the last example for today, last 15 minutes. Okay. All right, so let's say that we are computing free convection in a rectangular duct. Okay, so our duct looks like the following. Okay. Okay, and so just to make things a bit easier, let me kind of draw the cross section here. Okay, so the height of this duct is 0.3 meters. Okay. The width of the duct, L, is 0.75 meters. Okay. Surface temperature. Surface temperature is 45 degrees C. Okay. And the air temperature, right, so we know our fluid is air, T infinity is 15 degrees C. Okay. Right. And the depth of this duct into the page, we're going to assume is 1 meter. Okay. Okay. So another thing we're given in the problem, well, it's already kind of mentioned, but our air here is stagnant. And so there's going to be no forced convection. Okay. And so in this case, we want to compute the amount of heat transfer that comes from the duct to the air. Okay. Okay. All right, any questions on the setup for this problem? Okay. All right, so we have stagnant air, and so we know there's going to be no forced convection. So we are going to be looking at free convection here. Okay. Now we have a geometry here that we haven't explicitly seen because we have kind of a rectangular duct here. Okay. And so we haven't really dealt with this kind of directly with free convection. But if we split up this this geometry into its separate parts, you'll see we have kind of everything that we need. Okay. So step one, right? As is always the case with these convection problems, let's identify the geometry and the flow conditions. Okay. So first thing to note here is that, our solid here, or our surfaces, are much hotter than our fluid. Okay. So that's going to affect, the direction of fluid flow in these free convection situations. Okay. Okay. Now, in order to kind of break this down, let's consider each side of the rectangle as kind of its own separate plate. Okay. So I'm going to label each of the sides here. So I'm going to say the side on the left, there'll be side 1. The bottom plate will be side 2. The second vertical plate will be side 3. And the top plate here will be side 4. Okay. So if we consider each side of this rectangle as a separate plate, we can consider them as either a vertical or horizontal plate. Okay, so let's go through each side of the plate here and let's determine, whether they can be considered a vertical plate or horizontal plate. And for the horizontal plates, we're going to determine whether the flow is going towards the plate or away from the plate. Okay. Okay, so let's look at side 1 first. Okay. So side 1 is the left side of the duct. Okay. So relative to the direction of gravity, right? So we know gravity is going downwards like that. So side 1 here, we can actually consider to be a vertical plate. Okay.
Can I see how you numbered the sides?
Oh, yes. Yeah. Yeah, so basically go counterclockwise starting from the right. Yep, so side 1's on the left, side 2 is on the bottom, side 3 is on the right, and side 4 is on top. Okay. So side 1 there, because it is kind of parallel to gravity, we say that it's going to be flow or free convection on a vertical plate. Okay, now let's look at side number 2. So side number 2 is a horizontal plate. Okay. And for a horizontal plate, we need to determine whether the flow is going to be going towards the plate or away from the plate. Okay. Okay, so let's come back up to the figure here. And we know that we have a horizontal plate which is hotter than the fluid. Okay. So we have a horizontal plate here that is hot. Okay, so we know that when our solid is hot, it's going to cause the fluid to heat up. And so the fluid is going to become less dense and move against the direction of gravity. Okay. And so in this case, for side number 2, we have fluid that's going to be moving away from the plate. Okay. So that's going to be important when we choose our neutral correlation later. Okay, side 3, that's another vertical side, so that's going to be another vertical plate. Okay. And then side 4 here is going to be another horizontal plate. Okay. But again, we need to determine whether the flow is going to go towards the plate or away from the plate. Okay. Okay, so let's come back up to the figure here. And we know that our side 4, just like all the other sides, are going to be hot relative to the fluid. Okay. So that means fluid is going to be going upwards, which is going to be towards the plate. Okay, so if we break this down to the 4 sides, we have everything that we need here. So we're just basically going to be doing a convection problem just times 4. Okay. All right, any questions on how we identified these geometries here? Okay. All right. So step 1 out of the way. Step 2. Step 2 is we need to specify our film temperature and then evaluate our fluid properties. So our film temperature, just like our last example, is the average of our surface temperature and our fluid temperature divided by 2. Okay. And so in this case, it actually adds up to a very nice number, which is 30 degrees Celsius. Okay. And then just because we're going to need it to convert, we're going to need to compute beta. Let's compute this to Kelvin. Okay. And so we convert this degrees Celsius to Kelvin, we add 273. And so we end up with 303 Kelvin. Okay. All right, and if we look up the properties of air at this temperature, let's go ahead and write all these down. So we have, well, let's do beta first. So beta is going to be 1 over the film temperature in Kelvin. In this case, is 0.0033 Kelvin minus 1. Okay. We have the kinematic viscosity, which is 16.2 times 10 to the minus 6 meters squared per second. We have the thermal conductivity of the fluid. At 0.0265 watts per meter Kelvin. And we have our Prandtl number, which is 0.7. Okay. A lot of writing left to go. Okay. Let's speed run this. Okay. Number 3. Number 3 is we're going to compute our Rayleigh number. Okay, so let's do the vertical plates first because those are kind of identical. So this is going to be for sides 1 and 3. Okay. Remember, these are our vertical plates. And so this is fairly straightforward. So our Rayleigh number in this case is equal to gravity times beta times the difference in temperature, Ts minus T infinity. Now the height of a vertical plate was given by h. So this is h cubed, okay, divided by the kinematic viscosity squared, multiplied by the Prandtl number. Okay. All right, so we plug all of those values in. We have everything that we've kind of either looked up or is given to us in the problem. We get a Rayleigh number for our vertical plates of 7.07 times 10 to the 7th, okay? Which of course is laminar. Okay. Now for sides 2 and 4, so these are our horizontal plates, right? Eventually, to compute the Rayleigh number, we need to plug in some kind of length scale here, right? So remember, right before this example, I said that, for these horizontal plates, we have to use a special kind of length scale to plug into the Rayleigh number. So let's compute that first. Okay. Okay. And so this length scale is equal to the surface area of the plate divided by its perimeter. Okay. Okay, so to kind of assist with this, let me kind of draw our horizontal plate here. So this is going to be the same for both the top side and the bottom side. Okay, because we know that one of the lengths of our rectangle here was given by L in the problem, the 0.75 meters. Okay, And the other side is actually the depth, which we assume is 1 meter, okay? So that's the surface area under which our convection heat transfer is going to take place, okay? Okay, so we have basically the surface or the area of a rectangle divided by its perimeter. And so we plug in the numbers for this, we get 0.214 meters. Okay. And so our railway number, let me call this LC, okay, for length scale for the C. Okay. So the railway number in this case is G times beta times the difference in temperature, LC cubed, divided by kinematic viscosity squared, multiplied by the Prandtl number. Okay. And so we do all that, we get 3.64 times 10 to the 7. All right, so unfortunately, we are just out of time. So it looks like those technical difficulties we had on Tuesday kind of, took away the last 5 minutes I needed. But let me kind of outline to you kind of what we would do from here. From here, it's pretty much the same as we've always done. So step 4, compute the Nusselt numbers for each side. Okay. And so for each side here, they're going to have its own Nusselt correlation. So, 1 and 3 are going to be the same because they're both vertical plates. But for sides 2 and 4, you need to use a different Nusselt correlation depending on the flow is going towards the plate or away from the plate. Okay. And then once you have the Nusselt numbers for each side, step 5 is to compute their convection coefficient. And then once you have the convection coefficient, you can then compute the convection. Okay. All right. Any final questions before we head out for spring break? Okay. All right. So I apologize not being able to finish this example, but the details are in the lecture notes. So you guys can see them. So thank you guys for coming today. Have a wonderful spring break, and I will see you guys in almost 2 weeks.
I just wanted to double check, I think you said it right at that point, but the next midterm is April 14th.
Yes. So it's not the week we come back. It's the week after the week we come back. Yeah.
Okay.
Yeah. Because we still have to cover heat exchangers, and then heat exchanger is going to be on the second week. Yeah. Final is during finals.
April. Oh, I think it's 17th.
Not yet. Yeah. Once I do, I'll let you know.
Yeah, the Thursday.
Oh, yeah, I already have.
That's the Thursday, right, of that week?
Second midterm usually here.
I think it's easier from the sense that people kind of get a sense of what questions I'm going to ask. The content itself, I think, is hard. But I think people are just more prepared for the second one than
A lot of these steps, though, I feel like kind of just like the 1 through 5.
Yeah.
Go through. As long as you know the setup, I think the layout is.
Yeah.
More.
The thing that's hard for these ones is that these are more time consuming than the first midterm.
Oh, yeah.
And so usually what I do for the second midterm, I just give 2 problems. Just because there's just a lot more steps to do. Yeah.
So basically, as long as we know the geometry.
That's most of the battle right there for sure. Thanks, you too.
Yeah, once you're, it might be the.